The Indian Association of Structural Engineers, also known as IStruct-E, was conceptualized and constituted in the year 2002 by a group of senior professional structural engineers from all over the country. IStruct-E is registered under the Societies Registration Act 21 of 1860. IStruct-E is a national apex body of structural engineers in India with a mission to promote structural engineering profession and cater to the professional needs of the structural fraternity. In the short span of 2 decades, association has attained an eminent position in the professional field. Its membership is valued very highly in the profession. Since inception, IStruct-E has been led by eminent structural engineers like late Shri Mahendra Raj, late Shri Kumar Ghosh, Shri Subhash Chand Mehrotra, Professor Mahesh Tandon, Shri Alok Bhaumik, Shri Manoj Mittal and Professor R. Pradeep Kumar. As its president, IStruct-E is a permanent member of Engineering Council of India and interacts with the government on professional and policy matters related to civil and structural engineers. To expand its reach, IStruct-E has collaboration with various international professional like-minded associations and institutions. IStruct-E's prime objective is supporting and protecting the profession of structural engineering by upholding professional standards and acting as a mouthpiece for structural engineers in India. IStruct-E endeavor to ensure that its members develop the necessary skill in structural engineering and work to the highest standards by maintaining a commitment to professional ethics and standards. IStruct-E is actively engaged in organizing several continuing professional development (CPD) courses for structural engineers to help them update their knowledge and advance their career paths. It also conducts refresher courses for young and practicing engineers and student-oriented programs, seminars, workshops, conferences, technical lectures and discussions related to the latest technological advancements, and case studies are also organized regularly for members to enable them to continuously update their knowledge and skill set by interacting with the best minds from the industry. IStruct-E's activities are widely appreciated and known for quality technical contents. IStruct-E is also actively engaged in publishing its quarterly journal Structural Engineering Digest (SED), code commentaries, professional guidelines, and a monthly newsletter. IStruct-E's publications are becoming popular with time. IStruct-E has representation in various technical committees of BIS and IRC as well. Its members are actively contributing to National Code of Formulations. In the year 2020, IStruct-E started National Awards competition to stimulate interest in the structural engineering field and to promote innovative thinking and creativity. The awards are presented to the winners in recognition of their outstanding contribution to structural engineering in the categories which include Outstanding Structure, Outstanding Structural Engineer, Outstanding Woman Structural Engineer, Promising Young Structural Engineer, and Best Master's Thesis in Structural Engineering. IStruct-E is currently operating from 4 regional centers, namely Eastern, Western, Northern, and Southern, having its headquarters in Delhi to inculcate the professional culture and provide handholding to the budding engineers. IStruct-E has its student chapters in several leading engineering institutions as well. Membership of IStruct-E is open to all civil and structural engineers engaged in structural engineering profession. Members are elected based on their qualifications and experience in different grades as per eligibility requirements prescribed in the bylaws. Each application is carefully scrutinized before electing the members. More information about IStruct-E is available on its website www.istruct-e.co.in.
Good afternoon, everyone. Today, there is another webinar in the series of educational programs which we do. and this will be very interesting. The topic is diverse wind engineering requirement, tall building versus long span bridges. And we are very fortunate that Professor Prem Krishna is a moderator for this uh, course or lecture, who himself is very known for the wind and wind engineering. I don't think he requires any introduction as such for his experience and capabilities. So I request Professor Prem Krishna to take further this lecture on. Move on. Over to Professor Prem Krishna.
Good afternoon. Thank you very much, Mr. Pativar, for introducing me to the audience. As he has mentioned, we are looking forward to a very interesting lecture today from Dr. Suresh. And it's my privilege to briefly introduce him, although again, amongst wind engineers, he doesn't need an introduction. Among structural engineers also, perhaps very little. But as a formality, before we begin the program of lecture, I will briefly introduce him. Dr. Suresh is a vice president in an organization called RWDI, and without doubt, one of the most experienced wind engineers internationally. He has been working in this area for 35 years, handled different types of problems in wind engineering. A wide spectrum of structures have been studied in which he has been involved. Just to mention one, the Burj Khalifa being one of them. But there's just one of them. Also, it is interesting to just dwell a minute on about RWDI. RWDI is a firm specializing in wind engineering. Stands for Rowan, Williams, Davis, and Irwin, and has its headquarters in Guelph, Canada. It has facilities and offices more or less across the world. And without doubt, is the largest outfit dealing with wind engineering internationally. There are 5 wind tunnel facilities that it has. The 5th one is in Thiruvananthapuram, India. And this was established by Dr. Suresh, who nurtured this facility, established, nurtured, and worked there for almost, I think, 15 years or so, before he moved out to serve the RWDI from different locations, London and now in Dubai. It has been a pleasure knowing Dr. Suresh for all his years of wind engineering, almost from 1990, when he started his work in wind engineering at the Institute of Science, Bangalore. And then he moved on to carry out his doctoral work in Canada with another internationally renowned wind scientist, Professor Stratopoulos. And soon after, he has been into practice with the firm of RWDI. He has chosen a very interesting topic today. You know, we loosely talk about wind tunnel testing and forget about, what is involved in wind tunnel testing, where there are a number of fine issues, fine points. And today he's taking us into an area which we never think about, or not many of us will think about, how the testing of tall structures and wide span structures is differently placed as far as wind tunnel testing is concerned. So he'll compare the 2 kinds of structural forms for testing in the wind tunnel. May I, with this brief introduction, request Dr. Suresh to kindly make his presentation. All yours, Dr. Suresh.
Thank you, sir. Thanks for the kind introduction, and I think I had to also thank Sandeep for inviting me for this talk. I think he's the one contacted me. So let me share my screen. I hope you can see my screen. Can you see my screen?
Yes, yes.
Yes.
All right. So, well, I think having given a number of different talks on wind engineering, since because I won't be able to talk anything else other than wind engineering. So when Sandeep invited for this talk, and I was thinking, what should I be talking? Because I've been showing different slides all over India and maybe all over different parts of the world. So I picked this topic just because there's lots of difference between these two types of structures, and so I thought maybe it is good to look at this a little bit in detail. So just for your info, I have about 50 slides. I don't want to be talking all the time, so I would go through quickly, and then you guys can ask questions. So first of all, when it comes to these two towers, these two types of structures, I think the first thing coming to my mind is the weight of these particular structures. Okay, this is something you keep it in mind. The first two slides are probably the most important slides of the entire presentation. Mass. Okay, we cannot discount mass. So just look at these situations where bridges are typically very lightweight. Okay, 10 to 50 ton per meter. 50 nowadays it won't go to 50s. Okay. So it will be around, I would say, 30 ton on an average. Pedestrian will be less than 5 ton a meter most of the time. And then supports are only at the ends, contrary to tall buildings where gravity, is at our advantage in tall buildings. So this is, I think everybody has to pay some attention to this, the mass part and the connectivity. Immediately, what is coming to my mind is Airbus 380, because in many things, what we are doing is all adopted, a lot of things adopted from aeronautics. So when you look at Airbus 380, at the time of takeoff, the weight is around 550 tons, including fuel and people and etc. When you take this and divide it by the length of the Airbus 380, which is 80, so you can see immediately that this is more like a bridge type of weight that you are talking about. Okay, and the bridges are more like wings of an aircraft. And the weight is also very similar, I would say, very lightweight and etc. So that's why the bridges are getting into trouble most of the time, because first of all, it has no connections. Gravity is an issue. And then the other issue is the weight by itself. However, if you compare against a tall building, you can see this is the 42 in Calcutta, which has been completed. The weight is around 100,000 tons. And each floor is like one Airbus 380, actually. So you can see, imagine the weight of a tall building versus a bridge. I mean, bridges are very lightweight, okay, in comparison to tall buildings. So this is very, very crucial. So that is something that you have to keep it in mind. The second thing I thought I would also address about damping. So
Dr.
typically in
Suresh,
buildings.
Dr.
Yes.
Suresh, just a little interruption. I think I just wanted to inform the participant, whoever has a question, please drop in a question and answer box so that it can be taken after the presentation. Continue, please.
Okay. Next one is damping. So typically buildings, it's a little bit highly damped. So you can say 1% to 3%. This is again as an advantage to buildings. In comparison to bridges, the damping is typically between 0.3% to 1%. 0.3 is more like a very long span bridges, and then closing to 1% for shorter spans and things like that. So this is another biggest difference between the two. There are lots of other differences. For instance, if you think about the moment of a building versus the moment of, the acceleration of a building versus acceleration of bridges, very stringent criteria for buildings in comparison to bridges. Bridges are allowed to move a little bit more than the buildings for obvious reasons. Of course, you don't want to have buildings moving at a higher acceleration at the top of 100-story building, because you'll be scared and that's not allowed. So there are stringent criteria available there. And etc. I'm not talking particularly about that, but just keep this in mind, the mass and the damping. Okay, these are some of the things. I think when you think about these two slides, you'll immediately come to know that, okay, buildings having some advantages in comparison to bridges, definitely from wind standpoint. Now I move on to tall buildings first, and then I go through several slides and then move on to bridges. So when you talk about wind effects on tall buildings, primarily you're looking at buffering response. That is being underlined there. And you're also looking for vortex-induced oscillation. Most of the time, the response is mixed. You can't get purely vortex-induced oscillations. So it will be always mixed with buffering response. So if you look at the spectra, you'll see the spectra is not very narrow-banded. It will be slightly broad-banded with some spikes that is showing vortex shedding. However, it is mixed with buffering. So primarily, we are looking at these two things. We're not looking at other types of instability, which we are interested in bridges, like in torsion instability or galloping or anything like that. So it is all about buffering and vortex-induced oscillations. And when it comes to internal testing, most of the time you are going to do rigid models. So you can do high frequency force balance models, or you can also use high frequency pressure integration. In balance test, you're basically modeling the building and put it on a balance. And when you blow the wind, you're going to get moments and shears at the base, then you can distribute it along the height of the building. But when you do pressure integration, you can also get simultaneously pressure at multiple levels, and then you can integrate it to get the same. Actually, you can also get acceleration, floor-by-floor loads, etc. So overall, when you look at it, you're going to get mean loading and background loading from the wind tunnel, but you don't get resonant loading from the wind tunnel. You have to analytically compute it. This is a very traditional technique. There is nothing new here. This has been going on, I would say, for the past 3-4 decades. I think this method has been used successfully. Most of the buildings are getting tested rigid model. It will end there. We seldom go into elastic tests. However, in super tall buildings and very slender buildings, we do elastic tests. Like I said, a very few buildings have been tested, not few, certain amount of buildings have been tested using a elastic model where you can get all three components from the tunnel. You don't have to do any computation. So you can get a mean background loading as well as resonant loading from the tunnel. So I'm showing Burj Khalifa. At the time of test, we did a elastic test. I'm showing here the steel portion of the Burj Khalifa above 600 meters. We have done a elastic test along with the crane in place, tower crane. And you can see the ties of the crane going inside the Burj. So they were primarily interested in the interaction between the crane and the Burj Khalifa. So they would like to know what is the tie loads coming and how do they work in cranes during windy days, etc., etc. So we have been doing that test. So like I said before, you again point out one point, elastic tests on tall buildings are seldom done, very rarely, unless otherwise it is very slender and super tall. Now, if I go to the phenomena behind it, everybody knows the long wind loading, it is pushing the building in the direction of the wind. And you also know crosswind loading, you're getting some vortex shedding and building is oscillating across the wind. And we are primarily interested in these two along with the torsion. So if you look at the spectra, you'll see a long wind spectra and the crosswind spectra. The crosswind spectra is peaked. You can see that at vortex shedding frequency, there is a vortex being shed at a particular frequency, but your spectra is not too narrow banded just because it is mixed with the buffeting. So that's why it's a bit broad banded. You can easily calculate from the time series what is the bandwidth of your time series, etc. But in a long wind, it is purely broadband spectra. I think this is not something tall building people wanted. They wanted to somehow get rid of this crosswind using different shapes of buildings and etc., which has been tried a number of times in the past, for which again you had to do internal testing. So we have done such tests. This is Type A 101, one of our very old job. This is already existing for I think 25 years or so. We have done different shapes for this particular tower because square is giving huge responses in the crosswind direction. So the edges have been not chamfered. This is double step corner at the edges, which really help to, violate the coherence of the vortex shedding and improve the response. So you can see some of these graphs where you can see the left side graph. You can see the RMS value of crosswind reduced by 40% when you change the corner. So these kind of magics can happen when you change the shape of the building. But this needs to be confirmed through testing. There is no other way. We have done a number of them. I'm just showing you a few, which is being internal tested. This is Shanghai Tower. This is again a super tall building, 660 meters or so. We were given the opportunity to twist the building in different ways to reduce the loading. We have done a number of different models and tested in the wind tunnel. Finally, 120-degree twist gave the least load, and that's what got built finally. And there are advanced wind tunnel testing we do, but like I said before, again, underlining not for all buildings, but for really tall buildings. This is Kingdom Tower, which is under construction. We have done an elastic test over and above HFPI and force balance test. And this is, you can see the spine system in the middle, which is replicating the equivalent stiffness of Kingdom Tower. And this is the aluminum spine going all the way up without any joint whatsoever. So this has to be laser cut as a single piece, which replicates the equivalent model scale stiffness. And then you have to attach the shell around it and etc. The beauty of this is you can simulate higher order modes as well. And I'm giving a plot where you can see all the 7 modes. Well, yes, you can say 7 modes, and then how closely it is following the full scale results. So it is, you can get identical results as far as you do a good job in simulating the stiffness and the mass appropriately. We have done a number of model studies on birds. You can see the various models I'm showing. We started with the 1:500 air elastic, where we used a brass spine inside. And you can see various connections and etc. on Burj Khalifa. And this is about, you can see a 1.6 meter tall model. Then we also did 1:200 scale model, only for the top portion, the steel portion of it. And that is above around 600 meters. We have done with and without crane to understand the influence of crane onto the birds. And interestingly, sometimes we have to also do some large-scale model tests. Since we don't have the facility, we hired the NRC tunnel for a week to do this test. And this is only a portion of the birds. We cannot build the entire birds. So we did a portion of the birds, 1:50 scale. This is primarily done to check whether there is any Reynolds number effects, because birds has some curved surfaces. So we were kind of suspicious because at 1:500 scale, whether any violation of flow due to Reynolds number. And we improved the Reynolds number approximately 100 times when we went into this tower, but we didn't find any significant differences, so we didn't alter our test results. And this is another one, 11157 West Street. This is a very slender tower we have tested. Slenderness 24. It's like a pencil tower, already construction completed with a damper of about 600 ton towards the top. And this was tested multiple times again. I mean, air elastic, force balance, including HFPI, we have done on this particular tower. And compared the results against each other as well. And this is, what can I say? I mean, with 1:24, this is a marvel. The structural engineers, architects, they all did a very good job on this tower. And finally, it got constructed. So what I'm kind of insisting is some of these things have to be confirmed through tests. Initially, you can do some computational methods to do certain exercise to understand preliminary loads and etc. But eventually, it has to go to the tunnel and get it tested. And even after having nice shape and all the structural engineering, still it had higher accelerations. As you can see, initially the accelerations were quite high. Finally, they installed a damper, and they got like extra 4.5% damping or so through a damper, which was designed by us too. And we brought the acceleration down to even below the residential limits of 15, just about 15. The Shanghai tower went through large-scale tests as well. This is the entire tower, 1:85. You know the reasons why we did the test, like similar to Burj Khalifa for Reynolds number effects. So we just want to know whether Reynolds number is going to be changing our results or not. Because here we got again 100 times better Reynolds number by having a high-speed flow with a larger model. And these two had, I wouldn't say a great issue with acceleration, but still there were slightly higher accelerations. But with the help of a TMD, tuned mass damper at the top, which is about 1,000 tons, I think, which is again designed by our sister company, Motionary. And with the help of that, we could able to reduce the acceleration significantly. But most of these towers, wherever we are putting dampers, measurements are taken continuously in most of the time. I think one of the best one to compare is the Taipei 101, where the measurements have been taken since its inception, which is around 2000. And I think in most of the time in tall buildings, I mean, especially super tall buildings, there are lots of techniques that have been tried and to eventually satisfy everything. For instance, this is a classical case. This is one of the widely tested building in the world, I would say. This was in our tunnel at least for multiple times, and you can say for a span of 2 years or so. It's a huge job. We have tested this, I don't know, n number of times, I think, this building at various heights and things like that. So initially, our acceleration was about 37 milli-G, which is quite high. Then we did the HFFE with improved wind statistics. We looked at the climate in detail, and then we tried to tune the climate. We brought the acceleration down to 28 milli-G. And thereafter, we did the reorientation, reshaping, structural improvements, improved wind statistics. We got 19. Finally, with air elastic, we got 12. Okay. So this is how one can really do a wonder in terms of looking at each pieces very carefully. In those days, the reorientation is very easy because there was nothing there. We could orient in any way we want. So we were looking at from where the dominant winds are coming from, and the dominant winds were hitting the wings at the beginning. Then we asked them to rotate it by about 30 to 35 degrees so that it will come and hit the noses rather than the wings. So we could reduce significantly the loads and the response of Burj Khalifa. So that's the story of tall building. I just breezed through tall buildings. I think, what can I say in summary? Tall buildings are, I would say, need probably most of the time rigid model test, not really a elastic test. And you're looking at base loads, you're looking at floor by floor loads, load combinations, acceleration at the top, which is very important piece of finding out of the test. Because if this acceleration is exceeding certain limits, then you have to bring it down. At that time, you'll be playing with the geometry sometimes or structure properties. If both of these are not working, then you go for a damper. So that is typically the case. Well, most of the buildings are not having dampers, I should say. Very few buildings having dampers, but you need to pay some attention to these things, a lot of things. Now with the long span bridges, things are going to be a lot of different. So here, again, I'm going back to that piece of dynamic and static vibration issues, where here the interesting thing is we are more interested in galloping, torsion instability, classical flutter, etc. We want to make sure the stability of the bridge has been maintained first, before even looking at the response. Because there is no point in looking at the buffering response of a bridge until you make sure that your bridge is stable. And this is completely different from what we do on a tall building. Because in buildings, we never talk about stability issues because it's too heavy. It's extremely heavy. When you look at the Scruton number too, you'll realize how different they are actually. Because the Scruton number on buildings most of the time without the 4 pi and the equation is above 5, above 10, those kind of ranges. But in bridges, it's very low actually, because there's no weight and damping is also low. So this is causing a lot of issue, and that is why the stability is in question. So tall building versus bridge, tall building, no stability issues. And in bridge, there is a stability issue that needs to be confirmed. That is why the testing methodology and everything is different. Now I move on to some of the instabilities and where the vortex shedding is happening. Vertical motion is one of the issues. Like when wind is blowing, it can go up and down. And you could get a small hump at very low speed that corresponds to vortex shedding. I think if it is at very low speed, you're still concerned because you have to make sure that it is within the acceptable acceleration limits and etc. If it is higher speed, you're still worried because it is not about comfort, it is more about fatigue and other issues. So still it's a concern. You have to make sure that it is within limits and it can be manageable in design. The last one, you can see the circle, the red circle, you can see the response is going at a very high, it is exponentially increasing. That is because of unstable motions. Okay, vertical unstable motions is causing that, and we don't want to be in that location. So there are criteria out there, and today I'm not in a position to discuss that. But I think most of the bridge engineers might be knowing we want to have our such instability at very high return periods, like 10,000 year return period. If it happens beyond 10,000 year return period, then we are okay. Now, torsional motion. So in torsional motion, similar thing. I think the curve looks exactly the same, but it is due to torsional motion. Okay, it can go either way. There will be a twist, and it can take the bridge in both ways, twisting at the center, and that can cause excessive motions again. If there is negative aerodynamic damping and etc., I'm not going into, there could be even negative stiffness, okay? Negative stiffness and negative aerodynamic damping, which can all cause this torsional flutter situation. The hump which is on your left side, that is a vortex shedding hump still, but that vortex shedding will create the twisting rather than the vertical motion. So then you have the buffering. I think once those things are solved, then you're looking at basically buffering. At the time of designing the bridge, you're not looking at galloping or VIO or anything like that. You're looking at basically buffering response because you have been confirmed. I think you have already confirmed the stability of the bridge using shaping or whatever, I think, which I'll be covering. This is just showing the Tuckman arrows torsional flutter. So I'm not going to be explaining too much, but you can see large vortices shifting positions while the bridge is in motion. So that is causing some portion of the bridge being lifted up and some portion going down and then going in the opposite way and things like that. So few videos showing vortex shedding and flutter and everything. Primarily, one thing again, none of these you'll see on a tall building. Okay, none of the tall buildings are going to go through this. They do have some vortex shedding problems, but that is heavily mixed with the buffeting, and we wouldn't look at this. Of course, in tall buildings, when you have an antenna very slender above, and that can get into trouble, but not the tall building by itself. So the first line of test is section model test. That's what we do. We take a section of the bridge, not the entire bridge, and put it on rigs. So that details the model you can see from the models that I'm showing. It is designed in greater detail with everything, every flange and everything has to be X-bracing. You can see in this bridge, all the beams, X-bracing, etc., etc. Sometimes you may wonder, oh, this is underneath the bridge, whether you have to really model this or not. You need to model everything, every detail, including the parapet. You can see the parapet above, and that parapet is porous. Sometimes you have difficulty in modeling, at which case you had to make some assumptions and you had to have equivalent porosity. That's what I would call it. Equivalent porosity need to be modeled on the parapets. This is showing just a bridge model in section model. You can see a blip at the beginning, at the peak vertical deflection. That is a vortex shedding. And then if you go to the peak torsional deflection on the right side, you will see there is a significant increase in response, and that is flutter. But the flutter criterion speed is before that. So you understand, any bridge that you take, it can get into flutter. But as far as that response is happening above the flutter criterion, then you don't have an issue, because you cannot make sure that the flutter is completely not there. Sometimes it can be there, but you have to make sure it is happening at extremely high return period, so that, that wind velocity is not going to occur. And in terms of any stability issue or even vortex shedding issue, like in buildings, we have to change the shape, actually. So you can put end fairings, you can put baffle plates. These are all known techniques, okay? There's nothing new again. There are lots of other techniques have been applied already on bridges. I'm just showing two of them, and I'll show more as we go along. There are gate vanes. We have applied this on in one of the Indian projects, which I'll be showing. This can really divert the flow through this gap as well as outside. So basically our aim is to disturb the vortex shedding. We don't want to have any coherence in vortex shedding. And as far as you can disturb that, you can decrease the response. This is Golden Gate Bridge. After 85 years, we did the testing. The reason behind that is the suicide barrier. You can see the suicide barrier. They had decided to put suicide barrier, and on a bridge, you cannot put whatever you want after it got constructed, because at the time of testing, we assume the bridge is going to be like this, and we do the test. But later on, you say, oh, okay, I want to put a billboard on a bridge. That's not a good idea. On a building, probably you can do it, but not on a bridge, because your response can be completely different. And that's the reason this came for internal testing, because they want to put a suicide barrier. And when we did the test, we found some interesting motions on this bridge as well. You can see as if it looks like we are doing something, but the wind is doing the business. So it is getting torsionally excited in the wind tunnel. I do not know how we got the fix for this particular case. There are other examples I'm showing. This is a bridge in India where we had to do topographical model because there's significant topography around it to check the steering of wind flow. Maybe it is coming and hitting the bridge from underside or from above. So that got tested in a bigger tunnel. You can see all the topography modeled in 1:2000 scale or so. And then we made the measurements to understand the influence of all of these terrain conditions onto the wind speed at the bridge deck level. And these are those bridges. I think it's a twin bridge got tested in section model, and you can see some of the motions when we tested what happened. So both VIO and flutter, we got it out of this test. So when the bridge gets into flutter, we won't keep doing the test. We might stop the test because the bridge may get broken. The model may get broken. So in vortex shedding, it is okay because the motions may be slightly smaller, and then you can basically change the speed. As soon as you change the speed, the vortex shedding will stop. I mean, the response will stop. There's another case study, and this one is another bridge, which is more like a triangular cross-section, a little bit uneven shape bridge as well, where we did the test. We found a lot of issues, not significant issue, but there are some issues. So which you can see here, I think this is a 2D CFD we tried to do, and we found out that there's a big vortex shedding underneath is causing motions. And then we tried to remove that by putting a gate vane underneath the bridge so that you can see those vortices are gone. Just because the flow is getting through this gap as well as outside this gap, and basically that vortex shedding is not there. So we typically do these things in CFD in 2D scale, try to see whether this will work or not. And later on, we do the internal testing. And you can see that over here. And you can see the motion, what is happening. And those motions you can see on the peak vertical deflection as well. It is going above the criteria. The black line is the criteria. This is going far above the criteria. So we want to bring it down. And then we use the gate vane in this case to kill it. So you can see the peak torsional deflection below is not having that. And the red line is the mitigation. With the mitigation gate vane, you don't have such a peak. You can reduce it. And I'm giving a close-up photo of that particular gate vane being placed underneath the bridge to reduce these oscillations. You can also get force and moment coefficients out of this test. You can these models are dynamic models. You're putting it on springs. So it can vibrate, but you can also do static test on this. You can hold on to it. You can do static test and you can get these results. These are very important for your buffering analysis. You need to know the drag coefficient, lift, and moment coefficients, which you can use it for different calculations in buffering analysis. You can also get aerodynamic derivatives. These are dynamic tests again. You have to give an initial kick to the bridge, and then through system identification, you have to find out the H1 star to H4 star as well as A1 star to A4 star. Here, the question is all about vertical and torsion, not lateral motions. And these are all laid out items, which is part of the wind tunnel test. And every wind tunnel test, we'll be doing this. And these numbers, whatever you're seeing, the graphs and etc., has been utilized in the buffering analysis while calculating bridge buffering loads. There's another one, again in India. This is a quite wider bridge where we have seen some motion as well. And you can see how we solve this problem, because when we see these tests are quite time-consuming tests. When these things goes into the tunnel, typically minimum a week. Okay, you need minimum. If not, it will go beyond that actually sometimes. It can go to 2 weeks, 3 weeks and all. So it's a quite elaborate testing. And also you need to be having, the person who is controlling the lab should have a lot of patience as well. Because if you go too fast, you'll miss this. So you need to be very careful. There should be some expectation of this at what speed, and then you have to go back and forth slowly and try to capture this. So it's a interesting piece. And finally, we solve these problems through solid middle barrier. We increase the height because it had a barrier at the middle, but we increase the height of that barrier. And plus we also put 2 baffle plates underneath. So together this barrier and the baffle plates solve the problem. Okay, so we tried one by one, like solid barrier only without baffle plates, or with baffle plates, no barrier. But finally, we realized that both of these are required to reduce the motion. So you can see previously with the blue line, this is the vertical VIO. So the mitigated one is the red one with the help of those 2 elements. So even in torsion, we had a VIO, even though it didn't exceed the limits, but it is still quite high. But then we removed that using those techniques. And the last piece of this bridge study is the elastic test. You can see elastic model test of pedestrian bridge. This is the Dubai Water Canal footbridge. These tests are quite elaborate tests. So you can see in this piece, you have a deck, you have cables, and you have an arch holding everything, and every piece is elastic. Okay, this arch has a spine system inside. Then with all of these shells, and in between the shells, you can see a small gap of 1 mm or so. And this is required because the shell is not going to give any stiffness. The stiffness is given by inside spine. And these cables are spine as well, because this is a piano wire. And then the piano wire has these little, the wooden pieces attached to it just to get the equivalent area correct, because otherwise the piano wire alone cannot really have the correct drag actually. So we had to put these things. These wooden pieces are not going to create any stiffness. It is only there to create the effective area correct. And then this deck is also having a spine system inside, all the way in this shape actually. So this has to be cut like a single piece, most of the time without any connections at all. The connections are only these pieces that you see outside. That needs to have connections, because you cannot have a single piece. I think if you put a single piece of this external piece, then what happens is that will give you some stiffness. That will be quite difficult to manage it. So you need to have different types of systems. So you can see some lasers underneath and as well as vertically. So the lasers are measuring the deflections, and there could be accelerometers inside this arch that is also measuring accelerations. So together we can get all the deflections, accelerations, and even gauges. I'm not quite sure whether these are gauges, but you can also put gauges. We also do a lot of things during construction phases with the pylons. At the time of construction, it can be very unstable because you don't have any strut, you don't have in-between connections. You have 2 legs without any connections. So it could have a lot of problems. When we tested Takamanaras, we had issues on pylons as well. Then we had to suggest temporary solutions at the time of construction, like tie-down cables, temporary struts, etc. So again, this is a piece of the test we always do. Pylons in construction phases. What is the load coming onto the pylons? After construction with the struts and etc., probably most of the time it is very stable in comparison to bridge deck. This is another elastic testing of freestanding arch. I think this is a bridge in Iowa, USA. This is again, I mean, once you do that connection in the middle, then there's no problem. But at the time of construction, there could be problems. So they have done an elastic test for this case. This, you might be knowing, Miller Duct is one of the interesting birds. I mean, look at the shape. The shape is absolutely beautiful. It's an inverse airfoil shape. So if you think about airfoil, how the lift is created on a wing of an aircraft, this is more like a negative lift. Okay, it's not a positive lift, you know. Here the study, of course, we did a lot of studies on this. Not only us, maybe a few other labs as well done studies on this. But here, the sheltering, the wind sheltering, is a long bridge, actually multi-span bridge. So when the vehicles are passing through this bridge, it is getting affected by high winds, gusty winds. How to reduce the wind at the height of the vehicle? So using this kind of technique, I mean, you can see there's a sheltering done on the side like a parapet kind of a thing with some holes so that we can reduce 40% reduction on gust wind speed. And it is also maintaining aerodynamic stability and is also minimize the increase in wind loading as well. But primarily this is done for reducing the gust wind speed at the deck level. And this has been tested, even full-scale test has been done. I do not know exactly which tunnel it is not our tunnel. So you can see the 5 bar C cross-section, 0.3 meter wide and 0.3 meter spacing, and translucent. Obviously, people traveling would like to see, it's an absolutely fantastic terrain. So they would like to see the terrain as well. So that's why they made it translucent. We also do a lot of vehicle blowover study in the wind tunnel. And this is just to check whether vehicles at what velocity, up to what velocity we can allow the vehicle to pass through this bridge and etc. So lots of tests done in the past. We can measure the loading coming out to the vehicle. And I think I'm not going to go through a lot of details on this. However, I just want to point out that from IRC 6 2017 is something a little bit controversial. No live load allowed when deck wind speeds exceed 36 meters per second. All I can say is that it's a very high speed, and this needs to be looked at it. 130 kilometers per hour mean hourly speed. I don't think even beyond 70, 80 kilometers per hour, we'll be on the road actually. So this is something to be looked at it because it doesn't make any sense. And finally, this is my final slide. We have done one of the very long aeroelastic tests, long span bridge. This is 7 meter long Tacoma Narrows bridge. When the second bridge came, we had to test both bridges aeroelastic, the existing one as well as the new one. So we did model this for about 5 to 6 months by many modelers. We transported this to Ottawa, a 3-hour drive from Guelph, and we tested in a bigger tunnel, 9 meter by 9 meter, and to check everything is okay. This is a kind of a final test because after elastic, everything done. So we have done before CFD, analytical simulations, section model test, etc., etc. And then this is the final piece of test, which is one of the quite expensive tests in wind engineering. With that, I stop. I think I quickly breeze through both topics, and now probably it is time to hear the questions from the audience. Thank you.
Very fascinating presentation, Dr. Suresh. Very interesting to listen to you. And you so clearly laid down the important issues for investigating tall buildings or long span structures, bridges.
Yeah.
And very interestingly, you pointed out not a serious issue Instability is not a serious issue in buildings, but certainly bridges is very important.
Yep.
Also, I think it was very rightly pointed out by you that in most buildings, if we are not going for super tall buildings, the high frequency force balance studies may give you adequate answers, but if you
Yes.
have very tall buildings, you go for aeroelastic
Yep.
modeling.
Yep.
Likewise, in bridges, if you have medium spans, sectional model
Yes.
tests should be adequate, and
Yep.
you don't need a full aeroelastic model
Yes.
for that.
Correct. Yeah.
Construction stage studies, very, very important that you pointed out.
Yeah.
I think often we don't think about that the problem
Yes.
can occur during construction, but it can. You pointed out
Yeah.
about a bridge, towers
Yeah.
being in trouble during construction.
Yes.
I
Yes.
recalled another bridge years ago, the Fourth Road Bridge, a suspension
Road.
bridge in Scotland. While it was being constructed, they found that after the towers were up and the cables were in position, the towers started to vibrate with
Okay.
very large amplitudes and very uncomfortable to work on. So similar problems can occur. Very rightly, you pointed out the 36-meter requirement. Many of us have been talking about it and not very happy that it is still there, because 36 meters per second, nothing will move on the bridge.
Yeah.
It's not expected to move on the bridge.
Yeah.
So why
Well,
should the live load be there till 36 meters per second if it cannot be there? Yeah, that's
well,
a
if that,
valid point that you
I
raised.
think, interestingly, if that speed is coming, maybe we may even leave the city actually.
I can
Yeah,
add it
We may
here.
evacuate the city.
I just want to add here on this, Swapna, if you, if
ahead.
otherwise, Swapna, let Professor Prem Krishna complete his review, and then I will add special,
yeah, no,
typically for this
I
wind.
have no more views to add. I think if you
So
agree, Dr. Suresh, we can go to the question answer box.
I will go to the question answer, but see, for the wind speed, which is 36 meter per second, I think when we are drafting the code again, see, there was always an inquiry or the question that how much wind speed we should allow, and we wanted to take a references or see what is the Canadian code, what the Australian code, or what are the British code and all those things. But see, all those codes are actually very contradictory, and we could not actually get it very lesser speed. I understand that, okay, 130 km per hour is very high speed, but we want a, suppose if we want to put a some specification or some limitation in a code, we need a lot of substantial support from the either code or from the some study which clearly state that this kind of wind speed is not to be allowed with a live load. Actually, there's otherwise structure has to take that speed which is coming in that zone and area and all those things. But with the live load, this wind speed restriction should be limited. But let us actually we'll discuss it further when we are suppose some separately we can have another meeting, short meeting, and we can still
Yep.
further discuss about that. So
Yeah. The Chenab Bridge
yeah.
does not permit traffic after 25 meters per second.
But I think
Okay.
they might have placed us a sensor. I don't know how that sensor will work because it is a railway bridge, and there is the client agreed finally. Okay, so that my sensor capability, sensor monitoring, all those things is properly being done so that no rail will pass through that bridge if it is exceeding 25 meter per second.
Yeah.
So that monitoring and all those things is also very important if we such condition impose it.
I agree. I agree.
So,
yes, you have to go the whole way then. You
yeah.
have to ensure it.
Yes, correct. So, should I take one by one? I think apna question.
Please,
Can you
please go
see
ahead.
that question, sir?
No,
Uh,
I didn't
So
look at
I
the
think
question.
let me apna see. I think one first question is from Kanare, Dr. Kanare, and there are similar questions from others also. That whether the PPT PDF will be provided or not. So I think I request Dr. Suresh to provide us a PDF so that we can distribute to the participant by through their email, maybe after a couple of days, and where you feel that some presentation or some slides you don't want to present, then you can delete it and then present the presentation.
Sure, yeah, no problem. Yeah.
Okay. Then I think Abhijit Kulkarni also asked same. So it is okay.
Yeah, sure.
Now,
Yes.
okay. Now another question by Abhijit Kulkarni, that is, what would be the criteria of the tall building that would demand aeroelastic testing? So he is into the buildings, I think, and he is very eagerly want to understand this question.
Yeah, I mean, unfortunately, nothing in wind is written in stones. Anything that it is all flexible. Nowhere, I mean, it is said that beyond certain numbers, you should be doing an elastic test. So typically, elastic test is done. Let us say you have done all your logics in terms of shaping and you have done structurally, you try to tune the structure and etc. Now it is very imminent that maybe you had to put a damper. Then probably that is one of, and your acceleration is, let us say, around 25 or 22 or somewhere around that. In that case, maybe it is worthwhile to go into a neuroelastic test because that could improve the situation. Maybe you don't have a problem, because in most of the cases, when we have done neuroelastic tests on super tall buildings, it reduces the response rather than increase the response because with force balance, with the rigid body test, with analytical calculation of resonant loading, there are some certain assumptions you have been making. And maybe you can improve on that by doing aeroelastic, and you can get a little bit more realistic numbers, and then you can go. Let's say your acceleration is 50. Probably I wouldn't do it because you're nowhere near to acceptance. Maybe I can still do it and reduce the requirement of a damper. Still it may be. So there's nothing warranting to have an aeroelastic test. For instance, I can tell you another case where there's a 700 and plus meter building coming in. We have done testing, force balance, we have done testing HFI and etc. Everything looks okay. I mean, nothing, there's no significant crosswind or anything. Acceleration seems reasonable, slight exceedances here and there. However, since the height is being a little bit taller, I mean, beyond 500 meters, we thought that probably it's a good idea to do an elastic test. However, there are cases where 500-meter tall building, we have done a number of them recently. We didn't ask for the elastic test because everything is okay, so we don't have to do elastic.
I just add to the question of Kulkarni Abhijit only. See, maybe if it is a little bit different, but say when we decide about the wind tunnel test, let us say now whether it is a building or whether it is a bridge, I think I can understand about the bridges. See, because bridges generally we have given a some guidelines there. See some limitation in the height and some limitation of the span. Beyond that, it is necessary to do the investigate, and up to some criteria, say nothing is required to check it. So is there anything in a building whether wind tunnel test should be done like as in a bridges, beyond some span and height, and then the criteria, maybe frequency. Maybe
I think that's those criteria have been fluxed by different codes. For instance, if you look at the ASC code, it is 120 meters and your aspect ratio above 4 and period above 4 seconds. Okay, and under which condition you have to do a wind tunnel test. But then when you look at another code, maybe it is slightly different. Like for instance, in Australian code, I think it is 200 meters or so. Then with Indian code, I think with IS 16700, we got 150 meters. And that I am hearing that now that is getting pushed to 180 meters or whatever. I mean, so see, it is not the height which is going to drive this. I had to be very clear on it. Okay, the height
Yeah.
is not the driver.
Yeah.
Unfortunately, we are hung on heights all the time, and we say, "Oh, height is not playing a big factor." What is playing a big factor is especially slenderness.
Yes.
Okay, the slenderness is playing a big factor, and also the shape. Let's say you are coming up with a square and rectangle without any modifications or anything. We are asking for trouble. So there, you definitely have to do a test, okay, to figure out, because whether your surrounding buildings are helping your response or not. Sometimes surrounding buildings help, or sometimes it could worsen the situation as well due to wake buffeting. So
Dr. Suresh,
this kind of,
sorry.
yes, go ahead, sir.
Sorry, yeah, please go ahead.
No,
I
no, you go ahead,
asked
sir.
whether, rather than the height, should we go with
Slenderness.
the acceleration? If acceleration is
Acceleration.
higher than a certain, value, then you
You mean to say calculate acceleration first and then go for a test, or
I mean, that can be one parameter which should guide
that
us
can be
rather
one
than just the
parameter.
height.
We don't know the answer, right from the beginning, because when we come up with a building, we don't know what is going to be the acceleration on that building. So how do we know that? We can use certain codes to calculate it, but the codes are very kind of a crude equation. Sometimes you match, you'll be surprised that you match, but that is by chance, actually, by chance. So that is why the acceleration could be a criteria for aeroelastic test. I agree, because you already have force balance tests giving you acceleration, right? Then that could be a parameter for deciding whether you wanted to do aeroelastic or not. But at the beginning, whether to do a test or not, acceleration, I'm not quite sure how we can utilize acceleration.
I just want to add it here, something say, when we say the comfort of any structure, we always measure with respect to the acceleration, or suppose if it is a high-rise building. As you said, key one is the measurement of the acceleration, how it will come from the computational modeling and all those things is one subject. But suppose if we want to investigate a particular, suppose bridge or suppose structure, and then we feel, it is always a perception by the if suppose if a bridge is there and it is traveling on a vehicle, then it is a different perception. But if it is a pedestrian bridge, then it is a different kind of perception, because it is a direct perception received by the pedestrian. Now, how much is there any limitation from the acceleration kind of way for any structure that it is to be seen or it is to be
Yeah,
checked?
there are criteria already out there. I mean, these criteria have been already established. We are always kind of using the H2 criteria. I forgot 5% gravity below,
But
if I
that
remember
is that
correctly,
for
13 meter per
building?
second. Yeah, and not for building. This is for bridges. For bridges. Okay,
Okay.
below 13 meter per second, 5% gravity, below 22, between 13 and 22 meter per second, 10% gravity. This has been already established. And if you look at another code, maybe it could be a slightly different criteria.
Yeah.
But roughly, this is what we have been using for vortex shedding, especially for vortex shedding amplitude. But in buildings, things are different. In buildings, we are going with the milli-G. So in residential buildings, we talk about below 18 milli-G, 10-year criteria. And there is also 1-year criteria that depends on your frequency and etc. So there are equations given by ISO. Likely it will be varying from 8 milli-G to, let's say, 12, 13 milli-G or so. 1-year criteria. So you have to look at 1-year criteria as well as 10-year criteria. But in bridges, it's completely different. It is relaxed because the people are just passing through the bridge. Okay, they're not going to live there. So that is why you can be a little bit more relaxed, but not on a building. Buildings are quite stringent as far as acceleration is concerned. However, buildings having other advantages, like I said, I mean, too heavy and gravity advantage and all of those things are there.
I think Professor Prem Krishna has to, I don't know whether this guideline for the extra dose bridge and cable stay bridge have taken this into consideration, but if it is not, I think we can add this acceleration at least in a comfort for a structure, because I don't remember such criteria is presently in our code. Maybe in other code it may be existing.
I think there are specifications available for pedestrian bridges.
Yeah, pedestrian bridge is available. There is separate code is there, but I don't think it is for live load. Any such criteria has been mentioned.
No.
Yeah. So I think next I will go to the next question now. It is from again Abhijit Kulkarni. Would it be good to get Dr. Suresh view on the wind speed in Indian metros? I think we have discussed. But his further is asking that can the lower wind speed be considered acceptable if wind tunnel tests are done? So in my opinion, yes, it should be considered that way. But I think please give your opinion, provide your opinion.
So he's just asking my opinion on it, or is it?
So he's asking, I think your views. So it is on your views.
It's a very controversial topic. Okay,
Yes.
it's a controversial topic.
Yeah.
What I would say is that
Yeah.
Indian code, wind speeds, not just on metros, on the coastal regions, some of the metros and etc., have been high. Okay, so if I want to talk about Mumbai, particularly 44 meter per second is in Mumbai code. Okay, and without any K4 factor, the new cyclonic factor is not being applied there. But even without K4 factor, it is 44 meter per second. And when we looked at the Chhatrapati Shivaji numbers for a longer period of time, and including cyclones, because we did cyclonic simulation for 100,000 cyclones coming along the Bombay coastal region and etc., the speeds are well below 44, okay, well below. I would say even below 35. But see, we have to take a stand being a consultant. We don't want to go into very low numbers. So we thought that we were suggesting through a paper that we can easily take that 44 down to 39 because we have zones, right? So after 44, 39. So we thought probably we should go to 39. And that alone can save, like, how much saving is going to cost. I mean, this will do because that is 12% reduction in the speed, which is going to be like 30% in certain buildings. It can reduce the load by 30% on a lot of buildings, I think all the buildings. So this is see, you have to look at it in multiple perspectives. This is not just our prediction. We have been working in this region for a long time. We also looked at Sobel. There's another paper from MIT. They did cyclonic simulations in the Arabian Sea. They looked at the data. They have huge number of cyclones they simulated as well. This is a known technique. This is nothing new. Monte Carlo simulation has been widely used and tested in America. The coastal speeds have been decided purely based on Monte Carlo simulation, not based on measurement. Okay, not based on measurement. And what Sobel said is 200-year return period wind speed in Mumbai is going to be 36 meter per second. Okay, 200-year return period, not 50-year return period.
Yeah.
Okay, so all of this is pointing that this is the case. And plus, there are lots of other examples, which probably I don't want to delve into too much in this topic. This will be a topic of my presentation, the coming CTVOs in Mumbai, okay, where I'll be really deep delve into these details, because this is something the developers, the government, the BIS, everybody has to look at it very carefully, because we wanted to go in a sustainable way. We don't want to waste materials. It is not about savings, okay? We just want to do justice to our planet.
I have just one, I just want to add it. See, I want to take a view further of you. See, when we talk about the wind speed or whatever the reduction in suppose your modeling, all those things gives a better result, whether we can take it or not. So there are three things which comes in our mind or in everyone's mind whenever suppose we are building any structure. One is the sustainability. When we talk about the sustainability, we should not consume higher than the required, and it is really should be sustainable. Now, second part is the global warming, which is maybe affect, local zone, terrain, condition are the,
Understand.
Third thing is again, if na suppose in any such scenario, there are two parts are always there. One is a contractor side and another is a checker side. So he just want a kind of assurance whether the condition which is right now prevailing in a particular condition with a habitat condition right now, suppose in a Bombay, with a some terrain all around the building where suppose if a model is there for which winter test is being done, but there is a multiple buildings are there all around. Now that building, suppose if it is later on, suppose it is a hypothetical question, hypothetical thing, but if it is decided to demolish all those building around that building, or suppose if it is near the sea coast, suppose if there are some structures and trees are there, the plants are there, if it is a taken down and then gone away, then will it affect it? So then how to see, all those are contrasting. One, we talk about the sustainability. Second, we talk about the global warming. Third, we talk about the uncertainty. So how someone can address those issues? That question
See,
comes.
I think there's no question of fear in engineering, in my opinion, because we have to take the best decision possible with the given set of data that we have and the set of knowledge that we have. The global warming, for instance, I mean, if you look at all over the globe, look at the codes. In some places they have looked at it. For instance, in Canada, they looked at it in detail, where we are a part of it. We did a lot of simulations for global warming, looking at ocean currents and etc. And there are many other places things are happening. Okay. But then nothing is coming to the code, except you can say, for instance, if you look at the Australian code, for instance, they came up with a factor called climate. I forgot the exact name of it. They added a factor 105, 1.05 onto the speed,
Yeah.
if you're
Okay.
considering the coastal regions, zone C and D or something like that in the Australian code. That is the only code came up with that factor. But again, I mean, when we looked at those data as well, to tell you the truth, we are not convinced. Okay, we are not convinced because there is no justification. Because when you look at those cyclones, you have to look at those data from NOAA. There is data already available on the net. You can download and see, and you will see that the difference in number of cyclones and the intensity of cyclones happening in the northern hemisphere versus southern hemisphere. Southern hemisphere has very few cyclones, very few, okay, compared to northern hemisphere. So there's no justification sometimes for those kind of things. So which we are not part of it. We are not supporting that. But all I can tell you is that this. Look at what we have lots of information. Okay, already we know global warming. We have a lot of data and everything. Look at everything holistically and try to come up with the best answer what you can provide today. Actually, rather than increasing numbers is not science without any substantiation. Okay, that is my point, because that is looking like we fear of, because I keep hearing that cyclones came, roofs are lifted off, everything failed. You first look at your own engineering rather than look at the wind, actually. Because most of the roofs which are failing is not being maintained properly or not being screwed down, then obviously it is going to get lifted off. That is not showing anything about the intensity of the cyclone, actually.
I think I can further add here that see, most of the time it is not that somebody's R&D at that particular location can be applied directly without understanding at other location. So it is not necessary that what is happening in a southern hemisphere, same thing will happen in a other part of the globe. See, it is not
okay, that is a very that's a very important point. If let us say in US something happened, we shouldn't be trying to match what the US is doing, because every ocean is different, and Bay of Bengal is totally different, and Arabian Sea is entirely different compared to Bay of Bengal and etc. You have to look at ocean by ocean, and you have to look at location by location, not like putting all the data in a single basket and try to predict it. Those kind of things will obviously increase the numbers. It's not going to decrease the number. So we have to look at it very, very carefully. I told you this is a controversial topic. Maybe we should take
Thanks
it
for
another
your
time.
view. I think Abhijit
Yeah, this is
must
just
be
my
happy
view.
about your answer. So
Yeah.
your views, I will say. I will go to
Yeah.
the next point. It is from Pulkit Velani. He's asking, is actual response of building is compared with the test result mentioned in slide 18. I think you have to go to slide 18
Slide
to see
18.
that what is
Just a minute.
there.
Slide 18. Oh, okay. Slide 18 is Burj Khalifa.
Okay. You have to show it so that.
Just a minute. Just a minute. Just a minute.
Right, sure.
Yeah, this is slide 18. What is the
He's
question?
asking, is actual response of building is compared with the test result mentioned in slide 18. That's what he's asking.
No, we didn't test. We didn't measure it.
Okay.
We didn't measure to confirm this, but we do have other measurements though, like type A 101, which has been already confirmed that has been continuously confirming for the last 25 years.
Okay.
So there are other buildings we have done, not on this one.
Okay. I just want to put one my thought here. See, when we do the wind tunnel test and say we have observed that this much water shedding or what are the behavior of the structure is happening for what are the conditions which we are measuring it, and then buffeting response or whatever the things which we have done the test and then concluded with the shape change and all those things, it is reduced further. Do we do any instrumentation after the post construction and see that what is the change in the those changes are happening, or it is within that changes, or how it is there any such kind of studies available?
Well, I see you have to understand that these full-scale measurement versus wind tunnel test, there are a number of things already being done. There are, I think Professor Prem Krishna also knows there are lots of full-scale studies, Aylesbury, TTU, even cyclone testing station. There are a number of things happen in the past, okay? So it is kind of laid out principles in terms of how to do internal tests, how to do comparisons, etc., etc. This is an old story, okay? There's nothing new. So still we are comparing. And primarily this comparison is going on whenever we put a damper, especially. So when we place a damper, we would like to know the damper is doing the function it's supposed to be doing. So we keep measuring accelerations, try to do that plot continuously. And where it is exceeding our predictions or not, and etc. So that has been happening on a number of buildings. Not really based on the actual loads or anything like that. And plus, we also do full-scale measurements of frequencies, damping, and those kind of things on constructed building. Just as certain, again, how to tune the damper for that particular frequency rather than the ETAP frequency and things like that. So we still do full-scale measurements, but not to the extent of every single details, because that's not needed. These things have been already confirmed through multiple times.
Maybe
Actually,
bridges are such
doing,
structures. Yeah.
doing
Go ahead, sir.
full-scale measurements for wind.
Yes.
The very difficult part is that you may instrument the building, but you can't order a storm.
Yeah.
You may have to keep on waiting and waiting and waiting.
Yeah, waiting. Yes.
So it's a very difficult, it's a rather tedious thing to do.
Yes.
Okay. Nice.
Yeah,
So
please.
I will go to the next question. This is by
Go ahead.
Abhijit Vijay Gawai. How is the skill set of model analysis? What criteria to be considered? I think Dr. Suresh, you want
skill set of modeling.
I think he just want to understand that, see how you decide the scale of model when you do the model test for suppose maybe sectional model test.
I see.
Maybe I think he is not making it clear, but maybe this I am
Maybe I think the scale is primarily decided by the tunnel, not by humans. It's mostly that, because if I have a certain size of tunnel, the tunnel is built with a vision of certain scales in mind. And otherwise, of course, if you want to test a huge model, you have to be building a much bigger tunnel, and requirements are too high, the fan requirements, etc. The cost will go through the sky. And then obviously, as a consultant, we'll be questioning whether there is any need for that or not. Because if there is no need, then we will not be doing it. Okay.
I think
And that is why we thought, okay, if there is a need, we have a tunnel in Ottawa. I mean, 9 meter by 9 meter. We can hire that tunnel. We can do the testing. That is much more cost efficient in comparison to having one of those tunnels and go bankrupt.
I just want to, I think I remember when we were, planning about the Anjikar Bridge. I'm not sure that when you
Yes.
have shown this topography model is of Anjikar.
No, I didn't
not,
show.
But, see, I remember when we were planning of the Anjikar Bridge, where the topography mineral test is to be required.
Yes.
I think we have decided some scale which will take the all features around that bridge into account, so that when the wind will be from particular that height, when it will be brought back to the location, and then how its behavior is there, so that should be captured. So that is the way scale should be modeled. Suppose if any model test is there. So
not really. See, if you with the tunnel that we have, we can test a typical building anywhere from 1:100 to 1:500 is a possibility. But when you change the scale, you're also answerable to length scales and etc. and etc. So it is very you need to be very careful. And plus, if you do bridges section model, we are always between 1:30 to 1:80. There, the scale is too big. And because the scale is too big, you need to look at the spectra as well, because length scale is a problem. And plus, your spectra, high frequency part of the spectrum will be higher, and low frequency is not simulated, etc. and etc. There's a lot of other issues of that. Okay, so you need to decide based on what you're looking at it. There's no clear-cut answer, but section models are always between 1:30 to 1:80. Buildings are between 1:100 to 1:500. Elastic test of the bridges could be somewhere 1:100 to 1:200. Those kind of numbers coming to my mind. And for topographic study, 1:2000 to 1:4000, because you wanted to cover a wider area, like kilometers you need to cover. Again, you look at the situation, because
choosing the
everybody
material also, when you select some model and then some kind of that frequency or the property has to be simulated from that model. That also may be deciding the
I think now we are getting a little bit off topic, because in rigid model there is no question of material.
Question of yes,
because
I
a rigid
understand.
in rigid model is a rigid model, so you can build out a balsa, plastic, anything you want actually. But when it comes to your elastic too, there is no question of material, because you're looking at EI holistically. EI, okay, elasticity of concrete into I, let us say, in full scale, versus elasticity of aluminum with a new I for the model scale. So you're not studying about materials, and plus all their elastic tests and everything, all the tests that we do, everything is in elastic range. We're not doing anything in elastic range or anything. So we're not studying about material. So we can use virtually any material you want, actually, as far as it is not being deformed too much in the test.
Okay.
Okay.
So I think next I will go to the next question by Sanket Mali. Of what material Dubai Canal footbridge model is made up of?
I really don't know. Inside spine could be very well aluminum.
I think you
and
have
the piano
already,
wire is
piano
wire, and the shell is printed. That is just a printed shell. And then the parapet would be balsa wood. So there are variety of materials used on that particular model. So
Okay. So thank you for, I think Sanket Mali might have satisfied. Now next question by Pulkit Velani. Do RWDI use beam model of bridge to prepare elastic model for wind tunnel test? See, I don't know. It's just
I
maybe
think there is a different question. I'm not a structural engineer, by the way. I can't really answer that. So I remember in one of the case, we were provided with the different models. One is with a beam model, another one with another type of model. Then we are supposed to be taking one frequency from one model and take the torsion frequency from the other model, because they couldn't be putting together everything in a single model. I don't know which project it is. So we had an issue like that in one of those jobs. I think it's mostly a structural question, because for us, we look at the data rather than how you build a model in your computer, actually. So we review the data, and if there is any issue, then we'll be asking questions based on our experience, obviously. We are not structural engineers. Okay.
I just want to add some in his question only. See, there are a couple of things which comes in my mind now. See, I think 3D printing is people talk about. So do you use that kind of machines,
Yeah,
for
we do. We
model
do. We
preparation?
have 8 of them in our office,
Okay.
large ones. So we continuously using 3D printers.
Okay. And second thing, when suppose someone is giving a frequency of any structure, maybe it is for a bridge or for it is a building. So do you have your independent, analysis tool where you just find out when you do the simulation and find out that such kind of frequency is coming? No, you just rely what
No, we
coming
don't.
from the
We
structure
don't do.
and then.
Sometimes we are given with the SAP model and ETAB model and etc. But we don't want to take ownership of that, because like I said, I mean, we are not structural engineers. But as soon as we saw your numbers in terms of frequencies and mode shape, definitely we'll have questions, because that is just because we have been seeing number of other structures. So we would wonder why you're not getting this, why you're getting such a low number, why your mass is too high, etc., etc. But that is purely out of our experience. We'll be asking those, and as far as we get a reasonable answer, then we are on the same page.
Thank you. See, there is another next question I will take. How many accelerometers are required to capture oscillation of the displacement in all 3 directions? I think he's talking about when you are doing a model test.
Yeah, see, in buildings, we always put 2 of those at multiple locations. For instance, in tall buildings at the top, at 2/3 height or a little bit down or whatever, we can put accelerometer wherever we want, but in 2 directions. Some accelerometers are like you can measure both in a single piece, but we are not using that many times. We are using separate accelerometers for each direction. Okay, in bridges, we do multiple techniques. We use accelerometers. We also use lasers. Wherever we want, we put lasers with a pointer so that we can get the deflections, and that is sufficient. Then you can create the rest of it. You can create acceleration, you can create loading, anything you want, you can create out of that.
Thank you. See, I think it is well answered. So I will go to I think there are still 1, 2, 3, 4, 5, 6, 7, 8, 9, almost. It doesn't so.
I think we can move a little faster now.
Yeah, a little bit faster.
Yeah, move a little bit faster, so that I think I have to be out
Because
by 4:30.
after each reply, another 2 question comes. Maybe it is like that.
Yeah, I know. But I think they can always contact me anytime they want.
So we'll leave it for another 10-15 minutes, then we'll conclude.
Yeah,
So that then
yes,
if suppose they
no
are
problem.
not
Yes.
answered, we will reply to them.
Yeah,
We
no
will
issue.
send those things to you.
Yeah, thank you.
Now it is a question from Sanket Mali. If a material other than concrete is used, then how scaling of mass is ensured? I think you are not doing a concrete modeling. You are doing a
No,
plastic.
see, none of the models are with concrete or anything. Most of it with plastic, balsa wood, aluminum, brass, etc. Right? So here we are not talking about material. We are talking about the mass, and we are scaling the mass. We are scaling the stiffness, and we are scaling the stiffness like you remember EI. Okay, EI is the number. We divide that EI with a particular scaling number. We get an equivalent EI in model scale. Okay. Then we decide, okay, we want to use aluminum and divide that equivalent EI divided by the E of the aluminum. Then you get I of the model. And then you play with the I of the model for your spine. It's as simple as that. It's nothing, no
I just
complication.
want to add one query here. See, when suppose if there is a initial frequency and all those things, it has been given by the some engineer to you, and now there is a some maybe geotechnical investigation is further done, and then there is some changes, maybe 10%, 5%, and all those things. How much really it affects your in-winter testing? It's suppose if it is done already.
You mean to say impact of foundations?
No, I mean to say
Soil?
of the suppose some frequency or something, some changes might
Oh,
happen.
something changes.
Yeah,
Okay. So
yeah.
I think in buildings, we are always doing sensitivity study. When we
Okay.
produce the report, we are doing plus or minus 20% what will happen to the
Okay.
structure.
Mhm.
So that has been done. But in bridges, that is not very typical. In bridges, we just provide whatever results you are getting. We don't because you know the complication. Too many frequencies involved, too many mode shapes. So we don't do any sensitivity. But in buildings, it's quite easy because you're dealing with only 3 fundamental modes.
Thank you. There's one question from Nishi Gupta. I think she wanted to understand. I'm facing problem in making an aeroelastic model of bridge deck section model. So can you briefly explain how to start calculation required for this? So maybe it is
Interesting.
you wanted to understand the aeroelastic modeling requirement. I think let us.
I think that's a bit more than I can explain in
Okay.
a place like this, I think.
Yeah. Okay. 1 second. Okay. Just 1 second. This we will reply later. Can you educate us about wind tunnel test done on Chena Bridge? I think Chena Bridge was not done.
No, we didn't do the wind
So
tunnel test.
I will skip this question. What are your thoughts on integrating SHM for better understanding behavior response of bridge and building during high wind?
SHM.
SHM, seismic harmonic motion. I don't know what is the meaning.
Structural health monitoring. Are you talking about structural health monitoring?
Oh, maybe
structural health monitoring may be the correct thing. Yeah.
So what is? Can you repeat that?
What are your thoughts on integrating structural health
SHM.
monitoring for better understanding behavior response of bridge and building during high wind? I think we have already replied that question in the sense ki are we monitoring further any structure or the bridge? So it is generally not all, but say some kind of studies are done in some buildings.
Yeah, I think
and those.
See, for knowledge, definitely this is very, very useful. There's no doubt. Okay, absolutely fantastic to have full-scale measurements. But you have to also understand that not just putting some accelerometers and computers somewhere and then go away and not doing anything is not very useful. So you need to also completely monitor that and try to come to understanding what is going on and things like that. And that is not happening. That is one thing. And second thing is, many private owners may not be really interested to monitor their building, actually. So I don't know, for whatever reason, it will be quite difficult to monitor some of the buildings. They may not allow it. But I think for knowledge-wise, I think I completely agree with that, because it is very good to know what is going on after construction. After construction, things are going to be different.
Yes.
It's not going to be what you do in a computer. Things are different.
But it has to be a very well designed exercise, complete
Yes,
A to
exactly.
Z kind of thing.
Yeah. Yes, exactly.
So next question, I will go to next question. Nonlinear time history analysis is suitable for such type of structure. Just make nonlinear time.
Yeah, I think it's more like getting into performance-based design. Now I think people are interested in performance-based design. I think particularly that is coming from seismic side of things, because in seismic, the forces are quite high and things like that. They have been doing performance-based design, but in wind, they already have a code. ASC came up with a code people started using that, but not too much performance-based design stuff is going on. But I think it will catch up, I think, along the way. See, first of all, the wind force is not extremely huge compared to earthquake. So that is one of the reasons where this is still not being completely, not being adopted in many designs. I think because if you look at the wind load, it is kind of 10% of gravity or so. In comparison to side swing load, can be a gravity sometimes. It could be as high as a gravity. We have seen earthquakes like that. So it's quite different loading, but this is something that we had to yet to see that is being captured.
I think it's in a very nascent stage.
Yeah.
The ASC also has a pre-draft draft,
Pre-draft,
It's not
yes,
even
yeah.
drafted. It's a
Yes,
pre-draft
exactly.
draft.
Yeah.
Yeah.
I think wind and seismic is a very different. So I think anyway, next question is, I think it is already replied. Hi sir, what are the major difference between rigid and elastic model which give best result? So I think this is pretty
Oh,
well.
I think this, see, always we do rigid model tests. We never get into elastic because in India, I believe in certain cases, we have been asked to do elastic on certain cases. But this is more like written somewhere in the contract that you have to do an elastic without even thinking that this is really required or not. So that is kind of a little bit, I mean, I can't take those. It's a bit difficult to accept it. The reason is, of course, as a consultant, I should be happy that I'm doing an elastic. But at the same time, I think we have to also think whether it's really required or not. So the initial test is an important test. And then later on, you decide whether you really want to go in such details. But that's not the way things are going, though, sometimes.
Thanks for your answer. I will go to the next question. Hi, sir. What are the major? No, so already this is replied. How to decide the scale of model for both buildings and bridges? I think this is we have replied. This question was from Divakar Kolibindi. So we have replied. Now, how to scale the model result to actual structure?
Oh, this is third semester fluid mechanics. Just go back to Buckingham Pi theorem and the rest of the non-dimensionalized numbers, which I also didn't probably attend those classes, but I later realized that it's too important, and nowadays I'm using it every day. So this is probably the easiest of all, okay, because you are measuring everything in minuscule scale. Very, very low numbers like 0.0054 or 0.0054 or whatever from the wind run. But eventually you are multiplying that with a huge number, 6, 9, 10 to the power of 9 and things like that. That is velocity scale square and your length scale cube or whatever for the moment. And then you'll get the prototype number. So this is what can I say, in layman's terms, this is scary because when you look at the numbers, you see, oh, you're multiplying with a huge number and your measured number is so small from the wind run. But I mean, this has been going on for years. I think
that is fluid mechanics.
Yeah,
that's
all
what
fluid mechanics.
I was thinking that, see, it is actually when we talk about the structure, it is the wind tunnel test is not a fluid mechanism also. See,
Yes.
because that interpretation comes from there. And that's one question I was thinking of. What is the difference between computational modeling and actual wind tunnel test? And when we think about the computational model, see nowadays everybody thinks that,
CFD is exactly like wind tunnel. CFD can produce exactly whatever the wind tunnel is producing. You're modeling the surroundings, you're modeling the building in detail, like in a wind tunnel. But the flow is going to be, you're simulating the flow and let the flow pass the body, and then you have to solve those equations, analytically, and then you're judging what is the load coming onto the building and accelerations and etc. Exactly the same procedure, but everything in a computer. Okay, and this is nowadays we are also using this. We have already developed this technique and we have been using this for preliminary wind load study. on any type of structure, we can do CFD, whether be it bridges or tall buildings. However, for final design, still we go back to the tunnel because we need a lot of validations and etc., which we are also doing it. Even now we are doing it. But it's not come to a stage where we can comfortably say, okay, we are done with wind tunnel, just use only CFD. We are not there yet. Okay, we are not there.
I don't know why, maybe I imagine in a different manner when suppose if we're doing a computational model, then your model is something fixed and then only surrounding fluid mechanism is working and then you are checking the behavior of the pattern and flow and then you are interpreting the result from that. However, suppose if you are doing a model, I think even the motion of the model also when the wind will be flow, then it will be have its effect which may capture or not capture. I really don't know whether it is required.
No, right now, no, right now with the CFD, what we are doing is the model is not moving. It's a rigid model. Okay. Then we are doing exactly like a rigid model wind tunnel study. That's what we are doing. If you want to do a moving model, things are very, very complicated because you need to have moving grid in computers as well. So things are going to be solving and the rest of it computer time and everything is going to be extremely difficult. Right now, what we are trying to do is on a rigid model, whether we can get the same results or not.
Okay.
Not on a moving model. That's why on bridges, it is not quite used. The reason is primarily this, because you need to have a moving model, moving grid, sorry, not moving model, moving grid and altering flows and those kind of stuff. So that they're not there yet.
So that's why so if there is a bridge for which we are doing the sectional model test and then it has a torsional instability and all those things, I don't know whether it will be able to whether we can able to see from the
no, not at this point.
Yeah. So next question is from Ramakumar Pechetti. In modern urban environments where metro viaducts and high-rise building coexist, wind channeling effects become a critical consideration because this structure create complex aerodynamic interaction. How this can be studied and analysis? I think he just feel that maybe the way you do suppose some kind of in a hilly area where a wind is coming
channeling
and channelized and then and then affecting any surrounding and all those things, whether such kind of things happen. Suppose there is a metro, so metro is in a particular way it is going some layout and alignment and the buildings are both sides. So at that location, and suppose metro is taking some turn, so but wind will not take a turn according to that, and then it may affect the structures surrounding that. That's my understanding when he's putting a question.
Well, I think, see, in wind tunnel, many things are possible. I mean, we have tested a lot of diverse structures and weird ones as well. So you have to look at case by case basis, what is really required. Then you carry out the test and you can
certainly this can be studied and analyzed. This is this can be, suppose if a particular location, if suppose somebody want to understand what is the effect of that, this certainly can be seen it.
Yeah.
So now I think this is question from Shubhankar Lohani. I think I will put a question like this. Do we need ductile detailing for wind load also? I think Professor Prem Krishna also replied this question. Do we need ductile detailing for wind load? Or maybe if suppose some column is there, I don't know. This is not.
No, I'm not. See, first of all, I'm not a structural engineering, but I never heard of ductile detailing for wind.
Ductile detailing is not required. It is only for seismic, where
also, indirectly, I think Dr. Suresh replied that question about performance-based design.
Yeah.
So I don't think we are getting into that area yet, as far as wind is concerned.
So there is a next question from Rakesh Kumar Shukla. When a wind tunnel test RCFD, simulation is mandatory and for which type of structure as per codal provision? I think this you have already replied. So I will go to the next question. It is from Mahesh. In IS code 16700, there is a guidance for wind load based on height of 150 meter and other factor like complex geometry, topography and natural period greater than 5 seconds. Considering other factor, what is the minimum height where wind load tunnel test is required? I think maybe Professor Prem Krishna may be knowing about this code. I don't know, 16700.
Yeah, I know.
It's a tall
Yeah, I
building
was
code.
part of that code.
Okay.
Dr. Suresh is part of the committee there.
Okay.
Code, yeah.
Okay.
Yes. I think that the 150 meter, I mean, we didn't do a lot of research to come up with 150 meters, I guess.
But his question is what factors what considering other factors, what is the minimum height where wind load tunnel test is required? 150 meters certainly is required, but where suppose there is some limitation of frequency. If you
Okay, I will tell you another example. There is a building, we are looking at only 80 meters and the base is 10 by 10.
Yeah.
So that's why this height is a very deceiving factor. We shouldn't be looking at height at all.
Yes.
So it is not a rocket science. I mean, 80 meters, your plan is 10 by 10. Now, why do you have to think twice on internal test? You're going to have a problem anyways. Because your aspect ratio is 8. Okay, so it's
You
very
have to
high.
look for aspect ratio and then actually
Yeah,
decide
aspect
that
ratio is the
whether-
main thing. Okay,
Yes.
there is another building in Mumbai. I think many of the attendees might be knowing Parel. There's a building 320 meters, and the base is 80 meters, and aspect ratio is 4.
Yeah.
So we knew in advance this is not going to have an issue actually. But we did the test, and just because of the height, not because of the aspect ratio, but we didn't have an issue.
Okay, so next I will take only 2 questions now, and then further things will close it. Or I will ask Prem Krishna to Professor Prem Krishna to close it. So next question by Deepti: How do along wind and crosswind effect differ in their impact on tall buildings versus long span bridges?
Well, I think these are 2 different structures because in the tall buildings, there is crosswind issues and it will increase load and etc. But as you know, the tall buildings are too heavy. But in bridges, there is no crosswind as such. I mean, you can say crosswind, you're talking about vertical stuff. Okay, vertical vibration versus torsional vibration. So it is more about vertical and torsion in bridges compared to 2 laterals in the tall buildings. So it's quite different, completely quite different stuff. And where the vertical coupled with torsion in bridges, and here, of course, here too, you can have torsion and sway coupled in tall buildings, but most of the time our issue is always sway, not really torsion.
I will go to the next question. From Ashish Gutipalli. Good evening, sir. As per IS 875 Part 3, the cost factor of building structure depends on the frequency of structure, whereas IRC code recommends to use G is equal to 2 up to medium span bridge. Is there any other code relating to the gust factor and frequency? I think Professor Prem Krishnan, do you want to reply this for gust factor on
I don't think there is a code which tells us what gust factor to take for longer span bridges. I guess you go by experience more than anything else.
No, what he's saying that in the IS code, the gust factor of the building structure depend on the frequency. That is true.
Right.
Suppose chimney is there, building is there,
you can compute
find out the frequency and then depend on the gust factor is taken. I think, Europe code, in my opinion, gust factor is given basis on some other factors and consideration. But I think they will see the new wind code, which will be coming out. There are some changes in a gust factor depending on the shape and whether it is construction is complete or not. I think there are some modification is done. And they will soon see.
I have one comment on that gust factor. The gust factor can only give you lateral load, okay? Because you're multiplying the gust factor with the mean load.
Correct.
get the peak load, okay? It won't work for your vertical loads, okay? Because the gas factor could be anything in the vertical load because you don't have a mean sometimes. Your mean is 0. So try to be careful. This gas factor business will work only in along wind loads in buildings and only in lateral load in bridges. There's no gas factor. I mean, we have been doing buffeting on bridges. We have seen huge gas factors on bridges on vertical and torsional loads because there's no mean actually. Mean is almost 0. So it is meaningless to talk about gas factor, especially on those kind of direction loading. You can only talk about gas factor in the long wind, in buildings, and only in the lateral direction in the in bridges.
Absolutely, I agree.
Thank you. Thank you for reply. I will
Thanks.
take the last question of this session today. And there are a couple of questions are remaining. I will ask IS Structure to send you so that you can reply
Yeah, no
later on
problem.
those
Yeah, no
questions
issue.
answer also.
Yeah.
I will
Yeah.
take a question from Dr. D.K. Kanare. Is there any thumb rule for deciding whether the opposite railing will be hit by wind? If suppose bridge has a one railing on a left side and another bridge on right side, and if it's a bridge width is 6 meter or 10 meter and 12 meter or 15 meter, typically railing is height, maybe crash barrier height is 1.5, 2 meter. And maybe
Yes.
bridge width is vary. Say sometimes it is a 10 meter, sometimes it is 20 meter, sometimes it is 30 meter. So is there any guidance, is there any thumb rule he's wanted to know?
How high this can go? That's a question.
The crash barrier typically goes maybe around 1.2
Oh,
meter.
crash barrier.
Yeah.
In the middle, you're talking. Oh, sorry, on
It
the
is at the
side.
end,
Okay.
both end of the bridge.
Okay. Well, I think if your crash barrier is solid and going too high, then obviously you may have some vertical oscillation issues. You can have flutter issues as well, because whenever we do test bridges, we have seen the crash barrier is one of the critical piece which is causing the bridge to be unstable. So we ask for the crash barrier to be replaced by steel barriers with porosity so that the bridge can be stable. So it's not a good idea to increase the height of the crash barrier because it will change completely the response of the bridge. That is because at the bottom side of the bridge is typically, I mean, at least in box cutter bridge, it is inclined and etc. to make it more aerodynamic. The blunt shape is coming right at the top actually because of the crash barrier. So the crash barrier needs to be looked at it very carefully. And we have seen multiple times, we asked for a replacement for that using porous barrier.
This question is little bit slightly different. He is asking if there is a one crash barrier on the left side of the bridge and another
left
is
side
the
of the bridge.
right side of the bridge also. So whether the wind will be considered on a both crash barrier or wind should come only one crash barrier and not other side of the crash barrier.
Because the bridge is, if the bridge is on a water, the wind can come from any direction, right? It can come from this
suppose
direction.
wind is coming from one direction, so one face is already obstructed and he has taken a wind pressure. Now another crash barrier is there, which is maybe at a 10-meter distance again. So whether that wind should be applied?
No, see, when we do the test, we are looking at the overall lateral coefficients, which includes both crash barrier and the contribution of one crash barrier versus the other crash barrier. If you wanted to know, then you had to do tests separately and find out. Like you can have one crash barrier.
No thumb rule. There is no such
No,
rule.
I don't think so. This is a little element. I mean, any element on this bridge could cause some problems.
Thank you.
Yeah. Thank you.
I think this is question answer is over. Two questions are there. I think that will send separately to you.
Yeah, sure. Yeah, no problem.
Can answer.
Yeah.
I request to Professor Prem Kushner to conclude this session.
Well,
what do you, sir?
There's not much to say except to again express my appreciation of Dr. Suresh's presentation. Very fascinating. And plus, the patience with which he has answered all the questions, sometimes questions being repeated also. But I appreciate that he very patiently went into the questions and he has given us a lot of basic understanding and information on the subject. I understand that if details have to be understood, you need more time and a different
Yeah.
kind of interaction.
Oh,
And I
yes.
think there are questions like that also, which were asked. So maybe another time, another way, we can get
Thank you,
answers
sir.
from Dr. Suresh himself
Yeah.
on those questions. But for the time being, let me say thank you, Suresh, for this
Thank you, sir.
very wonderful presentation. Thank you.
Thanks to both of you.
Thank
Thanks
you.
to everybody.
Thank you.
And
Thank
thank
you.
you all
very
the
much,
participants who came.
Professor Prem
Yeah,
Krishna,
sure.
to moderate this session, and Dr. Suresh Kumar to give such a nice lecture on to
Yeah,
us.
no
Thank
problem.
you.
Yeah. Thank you. Thanks, everybody. Bye-bye.
Thank you. Wish you a happy Diwali. I can say now.
Oh, wish you happy Diwali, everybody.
To all.
We will
To
meet
all,
again
yeah.
for the next webinar. See you soon.
Sure.
So that possible that
sure.
information will come to you.
Yeah, sure.
Thank you.
Yeah. Thank you. Thanks.
Okay. Bye-bye.
Bye-bye.